Hello everybody, and welcome to exercise 3 on page 11 of the workbook. Hopefully you've made an attempt at this problem. We're going to run through it together. So let's read what they're asking us. So they give us a set V. It's just the set of all ordered pairs AB, where AB and R are. And we want to define the operations of addition and multiplication in kind of a strange way here. So A1, A2 plus B1 and B2 is going to be A2 plus B2, A1 plus B1. Notice that the order has kind of been reversed from the ordinary way that we define addition. And then taking a scalar C and multiplying it by A1 and A2, we're going to get CA1 in the first coordinate and 0 in the second coordinate. This is a really strange way of defining addition and multiplication. We're going to see what happens as a result of making that strange definition now. Okay, so in part A, I want us just to do some calculations to get the feel for these strange operations that we've defined. So for example, how would we take 1, 2 and add it to negative 2, 3? Well, our definition of addition says that we're going to, in the first coordinate, put the sum of the second two coordinates. So 2 plus 3 equals 5 would go in our first coordinate. And then in the second coordinate would go 1 plus negative 2, negative 1. Okay, and the reason for that weirdness is the way that we defined addition up here. If we take that as our definition of addition, then that's the way that we have to add our vectors. Okay, and let's see, what about right below it? Well, same thing. If we want to take negative 1 plus 3, 4, we're going to first add the second two coordinates. Negative 1 plus 4 is 3. And then add the first two coordinates and get 2. Okay, and let's see, 2 times 4, 3. Here's our definition of scalar multiplication, and it says we're going to take 2 and multiply it by the first coordinate to get 8, but we're always going to get 0 in the second coordinate. Okay, so there's our 0. All right, and then finally, let's see, negative 1 times negative 3, 2 again. We're going to take negative 1 times negative 3 and get 3 in the first coordinate, and the second coordinate is going to be 0 by default, by the way that we defined multiplication. Okay. So, next question then is, we'd like to show that V is not a vector space with these weird operations that we defined. Okay, so in other words, we can define addition and multiplication in this strange way, but we kind of have to accept the fact that we're not going to get a vector space as a result of that. Okay, so how do we show that this is not a vector space? Well, basically, we need to demonstrate that at least one of the properties, the VS1 through VS8, is not true. That would show that this is not a vector space. And the thing about it is, there are a lot of the properties that fail. We'll just pick a couple and illustrate it. So my first claim is that VS2 fails. Okay, you can look back and see what that was on our list a couple of pages ago. That was the one that had to do with associativity. So to illustrate to you that that fails, let's do two kind of corresponding calculations here. Okay, I'm just kind of making some vectors up. You would probably show that this fails with other examples as well. Okay, and we're going to compare that to 1, 2 plus 1, 2 plus 1, 1. So notice that the only difference between these two lines is that we've grouped things differently. Okay, so let's do the calculation on the top line. So starting with these two vectors, which are grouped together, okay, if we use our strange definition of addition, we're going to get 4, 2 for that, which is then going to be added to 1, 1, and use our strange definition of addition again, and we're going to get 3, 5 out of this. Okay, so there's the result of our top calculation. Down below, we're grouping these two vectors together, so we need to do that addition first. So we're going to take 1, 2 and add it to, use our strange definition of addition down here, we're going to get 3, 2. Okay, use the strange definition again, we're going to get 4, 4. And notice that these are not equal. Okay, so we have just demonstrated that VS2 fails. If VS2 were true, those would have to be the same vector that we get. Okay, interestingly, that's not the only property that fails. Okay, let's look at another one that fails. VS5 also fails. Okay, let me see if I can convince you of that. So for example, if you took the scalar 1 and multiplied it by 2, 3, what we'd like to get is the vector 2, 3 back again, but notice, by our definition of scalar multiplication, we actually get 2, 0 out of this. The second coordinate is always 0, the way we define multiplication, and that's not the same as 2, 3. Okay, therefore VS5 fails. Okay, and then let me give you one more example of a property that fails. I claim that VS7 also fails. Okay, just to give you an example of that, suppose that we take 1 times 1, 2 plus 1, 2, and compare that to 1 times 1, 2 plus 1 times 1, 2. Okay, if VS7 were true, we should get the same thing out of both of those calculations. Let's do them separately and confirm that we don't. Okay, so up top, we're going to first add those two vectors together using our definition. That's going to give us 4, 2. And then 1 times 4, 2 is 4, 0. Okay, and then down below, let's see. We're going to first take 1 times 1, 2, which by our definition would be 1, 0. Okay, and then we'll get 1, 0 again. And by our strange definition of addition, that's going to give us 0, 2. Notice that those are not the same. Okay. And just make a comment. You could probably go down this list of our vector properties and find others that don't work as well. We just picked 3 off of our list and gave examples to illustrate that they're not true. Okay, now I want to ask you an important question at this point. Okay, so in order to prove that V is not a vector space, did we need to do all of this writing? Did we really need to do all 3 of these examples? If you think about it, it's enough just to show that one of these properties fails, so we could have actually stopped here. After we notice that VS2 fails, that would be enough to show that this is not a vector space, because a vector space has to have all 8 of those properties. Okay, so our final comment here would be for any one, okay, all we need is one of the 3 reasons above, V is not a vector space under these operations. Okay, and again, you could probably find other reasons, other properties that fail as well.